Welcome students to the module MOM 3602 Theory of Machines 3 at the University of South Africa. In this particular module, in this particular video presentation, we'll go through the examples that were covered in tutorial number 1 earlier on this month. The tutorial consisted of 4 questions, and let's get into it. So, question number 1 concerned a rod connected to some springs, and we had to derive the equation of motion for the particular rod, and using the equation of motion we had to derive the equation for the natural angular frequency omega n. There is a rod of total length L3 from point P to point Q. The rod is being pivoted at point P, and attached to the end point on the other side at point Q is a suspended mass. In between the pivot and the end of the free end are connected springs. There's a spring K1, a distance L1 from the pivot, and a spring K2, a distance L2 from the pivot, and gravity is acting in a downwards direction. We basically have to use Newton's equations of motion, alternatively Rayleigh's energy method, in order to derive the equation of motion. So, how do we do this, and how do we approach the particular system? Well, first things first, when we look at the system, we recognize that it is a rotational system, and there is a rotational displacement, and there is obviously a translational displacement for the end mass. Considering the definition of angle theta is arc length over radius, theta is s over r, theta is the angle in radians, s is an arc length in meters, and r is a radius in meters. We use the equation of motion to develop an approximation for the arc length. Rearranging the equation of motion, we have the arc length is the radius times the angle. Considering our picture, consider the point A. Point A is located a distance L1 from the pivot, therefore the radius is L1, and if the portion of the bar at point A is rotated by an angle theta, the deflection would be delta A is equal to L1 theta. S is equal to R times theta. S is delta A, the vertical deflection or arc length, which is approximation of the vertical deflection. L1 is the corresponding radius, and the angle theta is obviously just theta. So if we have the vertical deflection for the point A, this will stretch the spring K1 a distance delta A. Using our fundamental equations, the spring force, the retarding spring force, is minus the spring constant times the deflection. Therefore, the force exerted at point A due to the effect of spring K1 is just Fa is equal to minus K1 delta A. So, we've calculated the magnitude of that spring force Fa. But what is the direction of the spring force? In our diagram, we assume theta is positive in an anticlockwise direction. So, if theta is positive in an anticlockwise direction, and L1 is a scalar which doesn't have a particular sign convention, delta A will be positive or negative depending on whether theta is positive or negative. If theta is positive, that is to say the rod is rotating in an anticlockwise direction, the deflection delta A would be positive, and if theta is negative, then delta A would be negative. This means that if theta is positive, a positive deflection delta A would be in an upwards direction, and if a positive deflection is in an upwards direction, Fa is equal to minus K1 delta A would then be either positive or negative depending on whether delta A is positive or negative. If delta A is positive in an upwards direction, the retarding spring force would be in a downwards direction, and vice versa. So, by choosing a particular sign convention, we've automatically accounted for the direction of the retarding force. So, having calculated the retarding force Fa, so there is a point A connected to spring K1, we've worked out the deflection in an upwards direction, delta A is equal to L1 times theta. We've worked out the force Fa is equal to minus K1 times L1 theta, and then that force would induce a torque at the point P. So the torque is the force times the distance, technically the vector cross product of the moment arm times the force, and that particular torque would have a sign convention depending on whether the force Fa is positive or negative, because we are assuming Ra is just a positive moment arm. So without getting into too much details, we choose the sign convention in the following way. Positive translational forces are in the same direction as positive translational displacements. Essentially, if F resultant is equal to m times a, m is the mass, a is an acceleration, F is a force. If a is positive, then this would define the direction for a positive force, and if a is negative, this would define the direction for a negative force. We would then use a similar reasoning to work out a sign notation for positive and negative torques or moments, using the equivalent rotational form of Newton's second law. Torque resultant is I equivalent times alpha, where alpha is the angular acceleration and I is a moment of inertia. When we say moment of inertia, we mean specifically a rotational moment of inertia, where I is the sum of mass times distance squared, which is technically an integral. And then, obviously, using Newton's second law, we'd use a similar sign notation. Positive rotational torques are in the same direction as positive rotational angles. What does this physically mean? We look at the diagram over here on slide number 2. If theta is positive in a anti-clockwise direction, that means the torques of the moments are also positive in an anti-clockwise direction. Then, looking at point A, for example, if the deflection of point A is positive in an upwards direction, this means a positive force would be in an upwards direction. If there was a horizontal force moving towards the right-hand side from point A to point B, then the horizontal force would be positive in the direction from A to B. So basically, when we draw a diagram, and if x is positive towards the right, then positive horizontal forces are to the right-hand side. If y is positive in an upwards direction, then vertical forces are positive in an upwards direction. And if theta is positive in an anti-clockwise direction, then moments or torques are positive in an anti-clockwise direction. And that is the sign notation we'll use in this course, and that will make things very simple. In a similar way, looking at the point B, which is connected to a spring K2, the point B will have a vertical deflection. Theta is equal to S over R, therefore S is equal to R times theta. Delta B is equal to L2 times theta. We do exactly the same approach to work out the force as a retarding force and the torque, force times distance. Now consider the diagram where we have the hanging mass. We've analyzed the point A and the point B, the forces and the resultant torques. Now we have to look at the suspended mass, little m. What exactly does this suspended mass do to the system? Well, technically in this problem, it is referred to as what's known as a 2-degree of freedom system. What do I mean when I say 2-degree of freedom system? If we look at the particular equation, well, the particular schematic of the problem, we can recognize that the angle theta and the deflection y are sort of independent from each other. In other words, to describe the motion of the system, we need knowledge of both the angle theta and the deflection y. Obviously, the angle theta and the deflection y are somehow connected. We have to derive what is the connection for the particular system. And when we know theta and y, if we have knowledge of these particular quantities or coordinates, we can then basically derive the equation of motion for the system and the geometry and how the system moves based on the values of theta and y. Right. The challenge is how exactly do we work out theta and y? If we had only one coordinate, let's say theta, the system would technically be called a 1 degree of freedom system or single degree of freedom system, sometimes just abbreviated SDOF, single degree of freedom system. If we need more coordinates, which are independent of each other, but somehow connected, it is what's known as a multi-degree freedom system, MDOF. Brief comment when I talk about torques and moments. In this course, we'll mainly concern ourselves with two-dimensional problems or planar problems. In a plane, a torque is essentially equivalent to a moment, but there's obviously a sign notation, which we'll talk about a little bit more in a later stage. The resultant torque is I equivalent times alpha. Alpha is the angular acceleration, and the sign notation that we use for angles will basically give the sign notation for torques or moments. In simple terms, if we look at our picture for the original problem, if theta is positive in an anticlockwise direction, moments are positive in an anticlockwise direction, as I've already mentioned. Moving along, we then need to calculate the resultant torque for the system. In our diagram, there are torque components due to the spring K1, the spring K2, and the combination of the spring K3 and the suspended mass. We've worked out the torque because of the spring K1, torque A. We've worked out the torque for the spring K2, which is torque B, and the combination of the suspended mass and the spring K3 we'll call torque Q. So, for simplicity in this problem, we'll assume the suspended mass can only go vertically upwards and downwards. Technically, it will go in a type of arc depending on the magnitude of the angle theta, but we'll assume theta is quite small, 1 degree or 2 degrees, therefore the arc motion is approximately in a straight line. Remember that we said theta and y are independent of each other, and we fixed theta as positive in an anticlockwise direction, and for simplicity we'll assume y is positive in an upwards direction. This will keep things simple in our calculations. So, looking at our diagram, when the suspended mass m moves up a distance y, it will squash the spring K3, and separately the point Q, as it moves upwards or downwards depending on the magnitude of the angle theta, it will also either stretch or squash the spring. For example, if y is positive, we will squash the spring, and that will cause a retarding motion. If theta is positive, it will stretch the spring. If y is negative, it will pull the spring, it will stretch it, and if theta is negative, it will squash the spring. So there's a type of motion, resultant motion, acting on the spring K3. When we do this, we'll use Newton's second law. F resultant is mass times acceleration in the vertical direction. So we consider the suspended mass, the resultant force, mass times acceleration. Acceleration is the double derivative of displacement, and we fix the displacement as y in the positive upwards direction. Looking at the suspended mass little m, there is a weight component of a force acting in the downwards direction, and there's a spring force. And we basically do a vector superposition, and there is a string or cable connecting the mass to the spring, and in that string or cable there will be a tension. When we do a free body diagram, the weight will cancel with the tension, therefore the sum of minus mg plus t will be 0. So that gets knocked out in the equation, and we have m, double derivative of y, is equal to minus k3 into y plus L3 theta. So we say, so far, so good. Now, what is the force acting on the point Q? When we look at the diagram, there is a resultant force of the suspended mass, and in inverted commas, the force goes through the spring and then acts at the point Q. The reasons for why I can say the force goes through the spring is a little bit complicated, but in this course you can assume this is true. So there's a resultant force acting on the mass. It goes through the spring in inverted commas, and that force then acts at the point Q. We've got the equation for the resultant force over there. That force is acting at the point Q, and we assume the force is positive in an upwards direction. And if the force is positive in an upwards direction at the point Q, it will induce a positive torque, because the positive force in an upwards direction will cause an anti-clockwise moment. Therefore, that will be a positive torque on the system, and we assume by definition it is positive. It could be negative depending on the magnitude of y and theta. Y could be positive or negative, theta could be positive or negative. Therefore, the sum of y plus L3 times theta could be positive or negative. And depending on whether it is positive or negative, the force could be either positive upwards, 0, or negative in a downwards direction. So we say the torque at the point Q, due to the effect of the suspended mass, would be the resultant force, mass times acceleration, times the moment arm. For simplicity, we will assume that the mass of the rod, capital M, is not 0. If we do this, we can work out the equivalent moment of inertia for the rod. The rod moment of inertia at the endpoint is 1/3 mass times the length squared. The total length is L3. Therefore, the moment of inertia is 1/3 mL3 squared. Recall Newton's second law. Resultant torque is moment of inertia times angular acceleration. The moment of inertia is 1/3 mL3 squared. The angular acceleration is a double derivative of the rotational displacement, and this is the resultant torque acting on the system. Torque A plus torque B plus torque Q. We have an equation, and we also have an equation for the suspended mass motion. So there are 2 degrees of freedom in this particular system. In other words, theta and y are both necessary to describe the motion of the system. And we have a system of 2 simultaneous differential equations. In general, it'll be quite complicated to mathematically solve for these equations, either using analytical formulae such as various equations, or using transform methods such as Laplace equations and inverse Laplace equations. And it gets kind of complicated and messy. So for dynamics problems in theory of machines, when we have a system of differential equations, the correct approach would be to solve it numerically on a computer. In this particular course, we'll not focus on computer solutions of differential equations, because we are basically interested in formulating the equations. This is not exactly a mathematics course. So our main intention is to derive the equations of motion. So far, so good. So if we don't want to, or we're not able to numerically solve the equations, how do we analyze the system? Well, we can assume that because the spring K3 is not connected to the ground, when the bar rotates, oscillates by this angle theta, obviously it will drag the little suspended mass up and down, but we would assume that that mass, because it's not connected to the ground, cannot significantly alter the rotational motion of the rod. If we make that assumption, then we can, in inverted commas, uncouple the resultant motions. When we uncouple the motions, we can say the resultant torque at the point P, where the bar is rotating and pivoting, is just effectively due to the effect of the springs K1 and K2. In other words, the suspended mass just goes up and down. It doesn't really pull down on the rod. So torque resultant would be, under that assumption, approximately torque A plus torque B. We then put it into Newton's second equation. Torque resultant is I times angular acceleration. We have an equation. We rearrange that particular equation, and then we get an equivalent equation, M equivalent double derivative of theta plus K equivalent theta is equal to 0. This is in the standard form mass x dot dot plus kx is equal to 0, and then we can calculate the natural angular frequency as omega n is square root k over m. And that's the answer at the end of the day. This is how we solve the problem, by making physical assumptions and approximations, not numerically solving systems of equations which might be more complicated. In principle, if we had derived the full general equation and we made the assumption that the suspended mass was quite small compared to the mass of the rod, capital M, then if we follow through logically, we could still arrive at the same equation, but it would actually be much more involved and complicated. So this is more of an aside. It's not an examinable material, because in this course we'll mainly focus on pen and paper calculations and not so much on numerical calculations on computer. But if we have a system of equations, like this particular system of equations, in terms of the coordinates theta and y, second order differential equation, could be nonlinear, doesn't have to be linear equation. When we have that system, we can solve it on a computer by converting a system of nonlinear equations, could be first order, second order, doesn't really matter, into an equivalent system of first order differential equations. In general, in machine problems and dynamics and vibration applications, the equations will be nonlinear. It doesn't matter if the equations are linear or nonlinear, as long as we have a system of first order equations. It's quite possible to have a system of first order nonlinear equations. When we have such a system, we can use what's known as a fourth, fifth order Runge-Gotte solver to solve the system of nonlinear ordinary differential equations. Generally, in machine problems, it is easier to solve an ordinary differential equation than a partial differential equation. Ordinary differential equations can use ODE solvers, such as the Runge-Gotte solver or Euler solvers and other type of solvers, implicit or explicit. Partial differential equations is a more complicated topic that we will not cover in this particular course. We write a computer program to solve the particular problem. This is a program written in MATLAB. It will also run in Octave. Octave is an open source software that you can download for free on the internet. MATLAB is a commercial package. It's basically equivalent, it's just that MATLAB is much more polished, much more advanced, much more robust, and Octave is free software. So it is not as good as MATLAB, but in many problems it is just as good and reasonably good enough. When we solve the system, we can get some answers on the computer. We have a plot over here of the deflections for the angle theta on the top, which is the red, and the deflection for y, which is in blue. Essentially, when we look at the problem, we would like to solve for theta as a function of time and y as a function of time. In our analytical approach, we assume the effect of y is negligible, so we just solve for theta, and y is a separate issue. So we have the system, we have a rod, we have a suspended mass. The rod is rotating by an angle theta, which is a function of time. The mass is being translated by deflection y, positive or negative. When we look at the system, when we do a full simulation, the answer at the end of the day appears in the following graphs. The red is the deflection, the rotational displacement of the rod, in other words the angle theta as a function of time, and we see theta is basically going up and down. It is oscillating, in other words it is vibrating about the equilibrium point, and the deflection y is also oscillating. It is going up and it's going down. In other words, the rod is basically rotating up and down, up and down. It's going 0 degrees, it's then going 1 degree, it's going back to 0, then it's going back to minus 1 degree, more or less. And the suspended mass, while the rod is oscillating backwards and forwards, is also going up and down. This is intuitively obvious, and it is what we would expect in the physical problem. Now, I have to make a very brief comment about how we solve problems. When we solve vibration problems, we'll basically make the assumption that the system is initially in some equilibrium point. In other words, the bar is either horizontal or close to horizontal, and the bar is then vibrating or oscillating about this equilibrium point. It is technically possible to solve for the full system when it is not in equilibrium, but in this course we'll only focus on vibrations or oscillations about equilibrium points. This helps to make the analysis much easier. For students that have access to the Rao textbook, you can read more about it on page 132. For students who do not have access to the Rao textbook, you can look at the following picture on slide number 19. Basically, considering a mass in a spring system, the mass is stretched. In other words, the mass deflects the spring and it reaches a steady state, which is known as a static equilibrium position. And then after the mass stretches the spring, if the mass is perturbed, it will oscillate about the equilibrium point. This is essentially what happens in our original problem. When we do the analysis for vibration problems in particular, we will therefore usually disregard the effect of weight. In other words, the gravity force, because it will stretch the springs, the system will reach some sort of static equilibrium position, and then everything will vibrate about the static equilibrium position. So vibration problems are essentially relative displacements about some equilibrium point for the system. The question also asked if we could solve the problem using Rayleigh's energy method. Technically, we could use Rayleigh energy's method. However, there are actually two subsystems in the main system. When I say two subsystems, it's because there are 2 degrees of freedom, an equation for theta, an equation for y. Both of these equations will have respective energy terms. It gets a little bit complicated to combine energies from different subsystems. So therefore, in this course, we'll basically only use Newton's second law, where F resultant is mass times acceleration for an x direction and a y direction, and again Newton's second law for rotations in the angular theta direction. And that is basically the approach to how we would look at question 1. Right, moving on to question 2. It's a similar type of problem to question 1. There is a rod, there are some springs, but in this particular problem there is a torsional spring, KT, at the point where the rod is pivoting. So the rod is pivoting at a certain point. There is a torsional spring connected to it. Somewhere along the rod there is another spring K1. At the end of the rod there is another spring K2, and now there is the presence of a damper C1. The problem is basically to find the natural angular frequency omega n, and to explain why Rayleigh's energy method cannot be used to solve this particular problem. Right, how do we go about solving this particular problem? Basically, we approach it in a similar way to how we did in question 1. So, in the schematic, we have the spring K1 at some distance away from the point of pivot. We work out the vertical deflection using the definition of angle. Theta is equal to S over R, therefore S is equal to R times theta. For the spring K1, the radius is A, and therefore the deflection is just delta K1 is equal to A theta. There is a retarding force due to the effect of the spring. F is equal to minus K times the deflection, which is equal to minus K1 A theta. And then again, obviously, there is a torque. The force F is acting, we assume, in a vertical direction. Therefore, the spring force is in the opposite direction. And then we just multiply force times distance, and that will give you the torque due to the effect of the spring K1. In a similar way, we work out the deflection at the point where the spring K2 is. However, we have also in this particular part of the rod a damper. So, in a similar way to the first problem, when there is a force, we can assume in inverted commas the force goes through the spring and the damper. What this basically means is, in the schematic that we're looking at right now on slide 21, there is a damper and a spring on a certain side of the rod. Because the force is going through the particular system, we can essentially put the spring or the damper on the other side because it'll still experience the same force. So applying this logic, we work out the deflection for the spring K2 is the moment arm, total length L, angle is still theta, so delta K2 is L theta. The force would be the vector superposition based on the same deflection. The point at the end of the rod is undergoing some deflection. It will stretch the spring by this amount, and it will also induce a velocity in the damper by the same amount. So we then apply vector superposition. We work out the force due to the combination of the spring and the damper, and we take this force, we multiply it by the moment arm, and then we work out the torque due to the effect of this spring and damper. Then, for the resisting torque due to the helical spring, the KT at the point of pivoting, the generic equation is the torque is minus the spring constant times the angle, and this particular equation is valid for helical springs. Then we work out the resultant torque on the system, simply the vector superposition, and we just take the algebraic sum because each of these torques, torque K1, torque K2, and C1, and torque KT, have a sign convention. They could be positive or negative or zero. So we just take the algebraic sum of that, and this in our particular planar problem, two-dimensional problem, where vectors have algebraic signs, positive or negative or zero, we simply add them up. Looking at the rod is pivoting at a point. At the end point, the moment of inertia is 1/3 mass times length squared. So we just apply the formula, 1/3 mass length squared. Then we apply Newton's second law for rotations. For translations, F resultant is mass times acceleration. So force in the x direction is mass, acceleration in the x direction, or force in the y direction is mass times acceleration in the y direction, and then again the resultant torque in the angular direction is the moment of inertia times the angular acceleration. So torque resultant is I equivalent times alpha. Substitute the various formulae in there. We then have an equation. We take the Newton's second law. Torque resultant is I equivalent alpha. Put in the variable various terms into the equation. We rearrange the equation as a homogeneous differential equation. When I say homogeneous equation, I essentially mean all of the stuff is equal to zero. If it is non-homogeneous, the various terms with the differential equation would be equal to a non-zero term. We put that in the standard form, m equivalent theta dot dot plus c equivalent theta dot plus k equivalent theta is equal to 0. This is the generic standard equation that we'll study in this particular course. And then, using that equation, essentially the same thing as m x dot dot plus c x dot plus kx is equal to 0. We simply write down the formula, omega n is equal to the square root of k over m. Substitute the various terms for k and m, the equivalent spring constant, the equivalent mass, and then we get an answer at the end of the day. And that is basically how we would solve the problem. The final component to this particular problem was the query of whether we could use Rayleigh's energy method, and the answer is no. The reason for this is because of the presence of the damper. The damper in a particular system dissipates energy, and therefore energy in inverted commas leaks out of the system. Rayleigh's energy method can only be applied if there is conservation of energy. In other words, the total energy at a certain initial time is equal to the total energy at some other time instant, where the total energy is the sum of the kinetic energy plus the potential energy. The kinetic energy is fine as it is, however the damper dissipates some of that energy which is lost into the fluid for the particular damper. Therefore we cannot use Rayleigh's energy method. And that concludes the calculations for question 2. So just to quickly sum up, we have a system, we use various geometrical concepts and ideas. We work out the deflections for the springs and the dampers. If there's a deflection, we take the derivative, we work out a velocity. Therefore, we work out the retarding spring force and the retarding damper force. We say force times distance, that will give us a torque. We add up the torques, that will give us the resultant torque. Then we apply Newton's second law. Torque resultant is mass times angular acceleration. We get an equation. We then rearrange that equation as a homogeneous differential equation, like we have at the top equation, and that particular homogeneous differential equation is the standard single degree of freedom system for a vibrations problem. And essentially, once we have it in that standard form, we basically have solved to a very large extent the problem. So essentially the main challenge of modeling systems is to put it in the standard equation, and then once it's in the standard equation we can use our bag of tricks to analyze the motion, work out the damping factor, the zeta factor, the omega n factor, and so on and so forth, and solve the problem. And that is basically how we would go about solving question 2. Okay, now we come to question 3. This question is basically on a shock absorber system. Essentially, there is a system with a mass, a spring, and a damper, and based on certain physical characteristics for the system response overshoots by a certain amount, and we essentially have to figure out the damping factor corresponding to this particular condition. We don't have much information on the system. We have to make certain assumptions, follow through those assumptions, and see where it takes us to. So all we know is there's an overshoot of about 12.5%. Figure it out. How do we figure this out? We make some assumptions, and our first assumption is to assume the system is underdamped. In other words, the damping factor zeta is less than 1. Referring to the prescribed textbook by Rao, on page 161, we have a particular equation for the system response, x of t, as a function of the various parameters. Very quick comment over here. When we have a mass spring damper system, which is essentially the vibration system that we'll be looking at in this course, the parameters or the constants of mass, m, spring, k, damper, c, these three quantities are essentially equivalent to zeta, the damping factor, and omega n. We'll see how this happens at a later stage when we go through the course. In any case, in this particular equation, zeta and omega n are essentially equivalent or contain the same information as m, k, and c. So let's see how we can do it. We'd like to use this equation to work out the velocity, making a few substitutions. Just to make our life a little bit easier, we can write this big complicated equation as the same equation over there, where the various terms, for example, zeta omega n, that's just a constant, so we just call it little a. The other constant, 0, we'll call it capital A. The term inside the cosine, square root of 1 minus zeta squared omega n, again, it's a constant. So we basically make a few substitutions, and we do these substitutions so that we can calculate the derivative more easily. When we do the calculations, when we do a derivative of a product of terms, we apply the chain rule. Basically, the derivative of fg is equal to f dash g plus fg dash. in terms of time. So we have this very big complicated equation for the displacement. We put in our substitutions, we take the derivative, and we get an answer. This equation for the velocity is still in symbolic form because we don't know the particular parameters and quantities. Assume a few parameters: mass, a spring, an initial displacement, and initial velocity. In order to simplify our calculations, we'll write a computer program, and in this course, for simplicity and basically due to prior training, I prefer to use MATLAB and Octave. MATLAB and Octave are essentially equivalent to each other, as we previously discussed. So we put in our quantities, the known information, m and k on line 4 and 5, and then the various initial conditions for the system. And we follow through with that. We do some calculations, we simulate for a particular time, and then a little bit more computer code, we plot some results over there, we save the results to file, and then we look at the system response. Essentially, the top equation, the curve in black, is the system response for the displacement, x of t. So in the yellow dot, there's some initial time. At some initial time, t is equal to 0, there's some initial position, let's call it x0. The system is perturbed, it goes up, it overshoots, there's a green dot, and that gives you a maximum displacement. And the question is basically asking, what zeta value do we need for x max over x0 to be 12.5%? In other words, x max over x0 is equal to 1.12. The bottom curve is the velocity in red. We have the equation for an underdamped system. We have the formula for the velocity. We took the derivative. We've got this very big complicated equation. This is why we're using a computer program to plot the results. And we assumed certain initial physical constants, a mass, a spring, an initial displacement, an initial velocity to perturb the problem. We wrote a computer program, we plotted the results, and by using the computer program for various zeta values, we will get different answers. So, using the computer program, by putting in different zeta values, in this particular case, looking at our computer code, the initial part of the first few lines, initializing the workspace, clearing the variables, inputting some data, some parameters, and on line 14, we assume a particular value of zeta, which is 0.94. Using assumed value, we'll get some sort of system response, the black curve, and we'll get a ratio of the maximum to the initial point. We repeat a few values of zeta. Over here we see the equation 0.5, 0.75, 0.8, 0.9, various values less than 1. We get various results, and then essentially we will use these results as we see over here. In this particular case, zeta is 0.5. We get an answer 1.2808. Zeta is 0.75. We get an answer, so on and so forth. So for various values of zeta between 0 and 1, for a system to be underdamped, we'll get a black curve, a system response. And each of these black curves for various zeta values will have different results at the end of the day, as we see over here. Then, based on these various results, we can simply interpolate the data to get an answer. In this course, it's usually a good idea to use linear interpolation. Linear interpolation is essentially where we have data or information on two states, an x1 and x2, and a y1 and a y2, and we essentially join a line between the two points. This is a formula that we'll use for linear interpolations. Yi is the interpolated value, xi is the interpolated point. So we have an x1, we have an x2, we have a y1, we have a y2. We join a line between them. We choose an xi in between these 2 points, and we read off the value for yi. So this is the formula for linear interpolations. We have some data over there. We want to work out for 12.5% the corresponding zeta value. So this is the x coordinate, this is the y coordinate, which we want to read off over there. We apply the linear interpolation and we get an answer at the end of the day. So this is how we had solved this particular problem using a computer program. The question then asks a few other aspects. What happens if zeta is 3/4 of the original value? Well, then zeta is still less than 1. We can use exactly the same approach with our computer program, follow through, get an answer. That's fine. What happens when zeta is 5/4 of the original damping factor? Well, then zeta is technically 1.1778, which is bigger than 1. In other words, it's an overdamped system. What that means is, if we have an underdamped system, we can use this particular equation. And this will only work if zeta is less than 1. However, if zeta is larger than 1, that equation will not work, and we then have to use the generic equation where zeta is greater than 1. There's an equivalent formula for the particular case when zeta is exactly equal to 1. So this problem for question 3 is a little bit too complicated for pen and paper calculations, and it's more appropriate for solution on a computer, MATLAB or Octave, or Python or Excel, or whatever the case is. And in general, nowadays it is usually a good idea to be able to do computer calculations. Hand calculations are quite important in an exam. You would need to do some hand calculations. You'd also need to know how to do a certain amount of numerical analysis from some of your other mathematics courses, and a certain amount of mathematics. Derivatives, integrals, root finding, interpolations, a mixture of things. That it is how it is nowadays. You need a little bit of physics, a little bit of maths, a little bit of numerical analysis, a little bit of computer programming to solve practical problems in vibrations. And we'll take it from there and then move on to question 4. And we come closer to the end of the video presentation. So this is the final question, question 4, the infamous steam train, the Boston and Maine locomotive. This problem is basically, again, a type of shock absorber problem, and we need to do a few more calculations. So there's a train, it has a certain mass. The mass is 2,142 kilograms. It has some initial velocity, 8.9 meters per second, which is about several kilometers an hour. And the train is traveling on the track. The train then hits a type of shock absorber system, and we essentially have to design the shock absorber system to safely decelerate the train so the passengers in the train don't get physically sick or injured. The human body can take certain amounts of accelerations, so there's a difference between a velocity and acceleration. For the sake of argument, if you go on an aeroplane, a Kulula flight or Mango flight or South African Airways flight, and you go up in the sky, you take off on the runway, you then on cruise, and you're flying through the sky at a certain speed. This could be about 500 kilometers an hour, around about 800, 750, 900 kilometers per hour, depending on the type of plane you're moving in. So the human body can take constant velocities. It's not an issue. The problem is if there are accelerations, in other words, changes in velocity. In other words, this is known as G-forces. Jet fighter pilots can take about 6, 7, 8 G's, gravitational accelerations, before they get physically injured and pass out. And in certain cases, they can actually die if the accelerations are very high. The reason for this, it's a biological reason. It's basically because if there are accelerations in the body, these accelerations, to a certain extent, can cause forces. Force is mass times acceleration. So when the body experiences accelerations, they are, in a certain sense, a type of force. In other words, acceleration forces. So this is a physical reason why you would like to design systems so that there isn't an excessive amount of acceleration. So if you're in a train or a sports car or fighter jet or a space shuttle or a rocket, if there is acceleration, in other words, the change in velocity is very large over a very small amount of time, then there are very high g-forces and the body can sustain damage and injury. So this problem is basically to design a shock absorber system so the human body does not experience unnecessary damage. This particular problem is essentially a mass spring damper system, as we've seen in various other problems in the textbook, in the study guide, and so on and so forth. Physically, there are some practical considerations in this problem. When you have a spring, the spring physically, in many cases, is that of a helical spring. In other words, a wire of certain material properties, a Young's modulus, a Poisson's ratio, and the wire has certain geometrical parameters, a wire thickness, a wire length, and there are various formulae that you can use to work out the equivalent spring constant. Over there is a formula that you can see in your slide. K is equal to G, d to the 4th power over 8 dm cubed n, and there are various explanations in the question about what each particular term means. In many problems, we use strength of materials theory, which is basically a type of simplified theory of elasticity, where there are certain assumptions and constraints and limiting behavior. We won't really go into the details, just assume for the sake of argument that there are known formulae. In a similar way, using theory of fluid mechanics, mainly the Navier-Stokes equations, and lubrication theory, we can derive a formula for a damper. So a spring is basically a helical coil, and the helical coil gives a resisting motion when this helical coil is stretched or compressed, as the case may be. A damper is basically a type of plunger or piston that is moving in a fluid such as an oil in a larger casing such as an outer pipe or some sort of tube. So as the plunger moves in the oil at a certain velocity, based on the fundamental characteristics of the fluid mechanics of the system, there would be a resisting force, and the resisting force would be proportional to the velocity, and the constant of proportionality would be what we term in theory of machines problems as the damping constant, or the linear viscous damping coefficient. So we have various explanations. We've got some initial data based on the available resources for the train system and the oil and the lubrication and so on and so forth. So physically, when we construct a spring, we take a piece of wire, helical coil. Wire might be a misnomer, can be quite thick, 5 millimeters thick, 10 millimeters, 20 millimeters on certain trucks and spring suspension systems. So the details of how we physically manufacture the coil is not really important. It's more important to understand what is going on in the problem. And there is a way to manufacture and construct the spring, and there is a way to manufacture and construct the damping system as well. Moving on, the system is a little bit slow. It's not a problem. There's a lot of rotation, which is why the system is a little bit slow. Let's wait for the system to load. Okay, the system is. Let's go next page. Alright, so you've already got the questions in your My Unisa system, and the question is basically analyze the system and calculate the required interface gap. In other words, you have to design the damper So the damper and the spring, so the train experiences a certain motion and it exceeds a certain acceleration. There are some parameters to do sort of a scenario analysis. We won't really worry about the scenario analysis because it gets quite lengthy and time consuming if you're doing pen and paper calculations. So we'll just basically do an initial analysis, and the objective will be to understand how to go about to do an analysis for a system. This is basically a critical damping system. So the previous problems were underdamped systems, mainly in question 3, where zeta is less than 1, 0.5, 0.93. We worked out a particular value for zeta. In this particular problem, zeta is equal to 1.0. In other words, it's a critically damped system. There are other problems that you'll look at in your textbook for overdamped systems. So looking at slide number 40, we have basically a train which has a certain mass. The train is moving at a certain velocity, 8.9 meters per second, so many kilometers per hour. The train then impacts on a shock absorber system based on a spring and a damper with certain values. Essentially, we have to work out these values. And the entire system of the train and shock absorber system is effectively a mass spring damper system, and it has the standard equation that we see over here. We've analyzed this equation before. We've also commented that this equation with m, c, and k is effectively equivalent to a system with a omega n, a natural angular frequency, and a zeta, a damping factor. So the question makes certain simplifying assumptions. The question basically states the springs are in parallel. The reason why I asked the question in the way that the springs are parallel is that you basically add up all of the individual springs. So if a system with springs are in parallel, the effective spring constant is just the sum of all the individual springs, and when the springs are in series, the reciprocal of the effective spring constant is equal to the sum of the reciprocals of each of the individual springs. There are ways to analyze and derive that equation. I would suggest you through your textbook, the Rao textbook in particular, and you can also find some of that material in the Hanna and Stevens Advanced textbook as well. So I do this to sort of simplify the problem a little bit. We gave the formula for the spring constant, and then we substitute our known information into the formula to get another formula for the spring. K is equal to something times d to the 4th power over 8 d0, do, d minus d is effectively the mean diameter. We get a formula. Moving on, substituting the various formulas, the springs are in parallel. We effectively add up the springs, spring 1 plus spring 2 plus so on and so forth, plus spring 6. All of the springs are the same. Therefore, we just multiply it by n to get the equivalent spring constant. We substitute the known information into the formula that was supplied in the question to work out the equivalent damping value, C equivalent. And in this course, I would very strongly suggest that students consider using the SI system of units. The reason why I would suggest you use the SI system of units and scientific notation is that it makes things very simple and less complicated. The SI system of units, effectively a mass length time system, is in a certain sense a very simple system, more convenient system, a more practical system. So if you put everything in SI units, you don't really have to worry about conversion factors from centipoise to Pascal seconds, from newtons per millimeter squared to megapascals. Effectively, if you put everything in SI units, meters, seconds, kilograms, newtons, and so on and so forth, everything works out nicely, and you don't really have to worry about any additional conversion factors. So over here in the bullet points, I give you the information that is supplied, and I put it in standard notation in SI units. So effectively, you can take the standard data or information and put it into the formula without worrying about any conversion factors. So as I state in the solution, substitute the known information into the equation, and then you this will result in another equation with certain unknowns, as we see over there. So K equivalent is now a function of the unknown diameter, and we're waiting to load. The system loads. It's a little bit slow. I have a few other things running in the background. It's not a major issue. We do exactly the same thing for the damping constant. And then we have another equation. The mass of the train is constant. It's invariant. It's not affected by the damper and the spring. Essentially, the reason why we do that is because the mass of the train is so much larger than the mass of the spring. You can look at that in practical terms. If you have a car is about 1,000 kilograms or 1,400 kilograms, depending on the make and model of the car. And if you look at the suspension of the car, sure, yes, it can be quite thick, the helical coils, but the mass of these coils are substantially smaller than the mass of the total car. In the same way, if you look at the shock absorber system, the tubes that go into each other, the mass of the shock absorber system is substantially smaller than the mass of the car or the motorbike or whatever the case is. So effectively, we just assume the equivalent mass is just the mass of the train. So we've got the system, we've got a mass, we've got a spring, we've got a damper. This is in the standard form m x dot dot plus c equivalent x dot plus k equivalent is equal to 0. This is a standard single degree of freedom system that we'll use to analyze the problem over there. So using the standard form of the equation, we have omega n, just the square root of k over m. K is a function of the unknown, in this case the diameter d. M is just a constant, so we have a formula for omega n. Similarly, we have a formula for the critical damping value, Cc, 2m omega n, in terms of certain unknowns. Now, the trick part of the question is that it's critically damped. When I say it is critically damped, I mean zeta is equal to 1. Zeta is, by definition, the ratio of your damping constant to the critical damping constant value. Zeta is equal to C over Cc. We know that zeta is equal to 1, therefore C must equal to Cc. And then we have a way to formulate the damping value. So we put all of the information into the equations, we follow through. We then have a roadblock, so to speak, that we have two unknowns and one equation. So what do we do? Essentially, we apply good engineering judgment. We say, okay, we would like to physically construct a helical spring. Fair enough, there's a wire, a material, a diameter, and we also need to physically manufacture the damper. The damper is essentially a piston moving inside a cylinder surrounded by some oil. And the oil has some viscous property, it has viscosity, and the combination of the geometrical tolerance and the viscosity of the oil is essentially used to build up a damper. So to physically manufacture the damper, we have to turn a piston on a lathe. So we have a material, we turn the outer diameter, we have a boring machine or maybe a lathe with a boring tool to drill a hole, in inverted commas. It's actually a boring machine. You can't drill a hole to physically construct a damper unless you have a very specific small diameter for the dashpot. In any case, we've got a lathe, we assume a machining tolerance, and we follow through with these equations and we make an assumption. The assumption is that we can specify the machine gap to be 5 millimeters for the sake of argument. Then we follow through with this logic and these assumptions and we get some results at the end of the day. This is physically what the dashpot looks like. An inside piston, a solid. It goes inside a cylinder, a tube, pipe basically. We follow through. We have a result for the spring constant, K equivalent, 28,102 newtons per meter. We also then do the calculations for the equivalent damping value, 15,500 and change. Fair enough. So we've calculated K, we've calculated C, and we've already been specified what the equivalent mass is, essentially the mass of the train. So what do we do after this? Well, we need to check if our results are consistent. How do we do this consistency calculation? We effectively have to work out what is the damping value. So based on our calculations, we have to check if our damping value, zeta, is equal to 1. While the system loads, we do some calculations. Remember previously on the previous slide, we worked out the value for K, we worked out the value for C, we know the value for M, we then calculate the value for zeta. Zeta is 1.000000075, which is basically 1. So we've done some calculations, we made some assumptions, we followed through with the calculations, and at the end of the day, we get a value of zeta is equal to 1. And the system is supposed to be critically damped, therefore zeta is supposed to be 1. We see that our calculations are consistent. We know the mass, we know the spring constant K, we know the damping value C, we have the initial conditions, we assume x0 is 0. In other words, the train, we take our reference point as the point of impact with the train and the mass spring damper system. We know the initial velocity, the 8.9 meters per second. We substitute that into our general formulas. We work out an answer for omega n. We got the zeta value. We throw all of that data into the equations. We work out a formula for x of t, function of the time. We can take the derivative of that to work out the velocity. So we've got x of t, we've got x dot of t. This is a train, it has a mass, there's a spring, there is a damper. The spring force is by definition minus k times x. We worked out k, we've calculated x, we now have a formula for the spring force. We took the derivative before in the previous slide for the displacement, so we've got an expression, an analytical expression for x. Then we have an analytical expression for the damping force. We have to tabulate it for a few values. It's a little bit complicated to do it by hand, a bit time consuming, but we know that for a critically damped system, this hand-drawn sketch, this should more or less look like the system response. We don't know specifically what's the maximum time, but it's not really an issue because we can simulate it for any time. We can do this in a computer program. Again, MATLAB Octave for simplicity. We clear the workspace, we put in some initial time constraints, we use the for loop to work out the displacement x of I, v of I, we specify the k, the c, we then just multiply this by the displacement and the velocity to work out the spring force. We do some more calculations for the system. This is basically standard MATLAB code, nothing too fancy. Continues on a little bit, and then we basically see what happens at the end of the day. As I say, over here we can simulate the system for any particular time. We can simulate it for 5 seconds, 10 seconds. It's not a big deal. We can simulate it and then see what makes sense at the end of the day. So I do make the comment that it is quite time consuming if you're doing this by hand, not so much if you're doing it on the computer or on a spreadsheet, MATLAB, Octave, whatever the case is, which is not a big deal. So let's have a look at the system response at the end of the day. So in the top graph we have the displacement, in the bottom graph we have the velocity. Displacement is in the black line, the velocity is in the blue line. Let's try and understand what's going on in the system. So we're simulating it for a certain time, in this case 1.75 seconds. Initially at time t is equal to 0, this is where the train hits the damping system. The train then physically moves forward a certain distance, so as time goes on it goes physically forward. It reaches a maximum displacement. So the train starts, it physically goes to the right hand side a certain distance. The spring is pushing back, the damper is pushing back. The train physically goes to a certain distance towards the right hand side as it's going forward. the train comes to a stop, and then the train slowly gets pushed backwards, and eventually the train comes to a halt again. So this is the physical distance. It starts at an initial position 0, physically goes forward, it goes a maximum amount in the forward direction, and then slowly it goes backwards, and as it goes backwards, the relative distance from the initial point gets smaller until it eventually reaches the original point where it started. Let's look at the velocity. The velocity graph, this is the time, this is the velocity. The initial velocity is 8.9 meters per second, so that's the highest velocity. The train is physically moving forward. The spring and the damper are pushing back against the train, therefore the velocity goes down to 0. Eventually, at a certain point, as the train is moving forward, the train comes to a stop, and then slowly the train goes back. It slows down again, and eventually the velocity goes back to 0, and that is the end of the motion. Next, we have to look at the spring force and the damping force. So on the top graph we have the spring force, and at the bottom graph we have the damping force. Remember that the spring force is minus kx, and the damping force is minus cv, where v is the velocity. So initially there's zero displacement. We chose the initial point x is 0. This is x at 10 millimeters, 20 millimeters, so on and so forth. So as the train moves forward in time, the x increases, and as the x increases, the spring force increases, until eventually, as the train is moving towards the right hand side, it reaches a maximum displacement, and then it stops. At the maximum displacement, there's a maximum spring force. When the train stops, it then slowly starts to move backwards, and therefore the relative distance between the instantaneous position x of t and x of t0 gets smaller, and then the spring force gets smaller, and eventually as the train goes forward, it stops, it starts to go backwards, and when the train gets to the original point, the displacement is then 0, and then the spring force is then 0. So the train starts, it goes forwards, and then slowly starts moving backwards, and then stops. Looking at the velocity diagram, the damping force is a constant times the velocity. The constant is minus c. So initially the velocity is 8.9 meters per second. This is the highest velocity. Therefore, this is the highest damping force. As the train goes forwards, the velocity slowly decreases. The damping force decreases, and eventually the damping force becomes 0 when the train goes to 0 velocity and it goes back to the original point. And that is essentially of how the train system. Let's go back to the picture. As we go, we made various assumptions using the standard. Okay, going back. So as you see, this is conventional unit for viscosity, but when you're doing machine calculations, it's usually better to work with SI units, in other words pascals, seconds and time, and so on and so forth. So the train originally was on the track. It was traveling at 8.9 meters per second. It hit the damper, it goes forward, eventually it stops, it goes back slowly, and it gets back to its original position. And that is essentially the physical reasoning of what's going on, and we went through the mathematical details, and that is essentially how we do vibration problems. So to recap, we analyzed a sort of rod system, a 2-degree of freedom system. We approximated it as a one-dimensional degree of freedom system in question 1. We had another question in Question 2, where we did not need to make any assumptions, we solved it essentially exactly. In question 3, we had an underdamped system, and in question 4, we had a critically damped system. It is possible to have an overdamped system, and this is basically the approach you would use in some of your assignment problems and some of the exam problems. Thank you very much. And that is the end of the main questions. I may give a few minutes of demonstration of how to do MATLAB and Octave programming at a later stage. Thank you very much.